In this lesson, we're going to cover the last section in chapter 4, which is linear regression analysis. And I had explained at the beginning of chapter 4 that we could think of this chapter as being broken down into two parts. So the first part, we covered correlation. And then the second part now, we're going to cover the regression analysis part of it. So we said a correlation is just a relationship that exists between two variables, x and y. And specifically in this chapter, we're interested in a linear correlation. So we could either have a positive linear correlation or a negative linear correlation. And once we establish that there is some sort of linear correlation between two variables, then what we like to do is we like to develop a linear model that we could use to make predictions. So we could predict values for the dependent variable given a value for the independent variable. So in order to determine the linear model that will generate a close estimate of the actual y value, we obtain a line that best fits all the sample points on our scatter diagram. And we call this best fitting line the regression line. And the regression line is the same formula as a line that you're familiar with, right? When you guys think of a line, what formula do you tend to think of? Because there are different forms that we could use to represent a line. But I think one of the most common ones is y equals mx plus b, right? In regression, we use the same formula, but we just use different letters for the slope and the y-intercept. But we're still going to be using the equation of a line, y equals mx plus b. So before we go over how to find the regression line for a particular data set, I just want to review. So let me just open the whiteboard, and then I want to just review some important characteristics of a linear equation. So like I said, I think the most common form of a line that people tend to think of first is y equals mx plus b. And try and think back and tell me what are the coefficients? What do they represent, right, in this line? So we have m and we have b, or the parameters, we could also call them. So we have m, which is equal to the slope, and b, which represents the y-intercept. And the slope and the y-intercept are going to be significant once we come up with these equations that are going to model our relationships in the next few examples that we do. So I want to make sure everybody's comfortable interpreting these parameters of a line function, meaning the slope and the y-intercept. So let me give you an example. Let's say we had the equation y is equal to 3x plus 2. So in this case, my slope, which is m, that's equal to 3. And the y-intercept is equal to 2. So what does that tell us about the line? Well, the y-intercept is where the line is going to cross the y-axis. Now, in order to cross the y-axis, so here's, let's say we have a coordinate system. Here's x, here's y. Wherever the line crosses the y-axis, we call that point the y-intercept. So I'm just going to draw a couple of different lines here just to give you examples of y-intercepts. So we have 3 different lines here, 3 different y-intercepts, and I want you to think about, what does each one of these y-intercepts have in common? The y value is different for each one of these points, but the x value is the same. It's 0, right? Because we're on the y-axis. We didn't move left or right in the x direction. So each one of these points, which is a y-intercept, but they also have the same x value, which is 0. So we can think of the y-intercept as the point 0, comma, b. And b, remember, in this case is 2. So my y-intercept is 0, 2. So that's going to be the point on the graph. So when x is 0, y is equal to 2. Now I want to interpret the slope as well. So slope is just a rate of change. It's specifically the change in the y values with respect to the change in the x values. So you always want to think of slope as a rate of change. Now in this case, my slope is equal to 3, but we want to think of it as a rate of change. So we want to think of it as a fraction. So 3 is, and I'll write it this way. So we could think of it as 3 or 3 over 1, right? 3 over 1 is the same thing as 3. So what we could say is for every 3 values that y increases, x is going to increase by 1. And that's why you guys were probably taught in the past rise over run, right? So think of the numerator as the change in the vertical direction, and the denominator is the change in the horizontal direction. So for every 3 units that y increases, x is going to increase by 1 unit. That's how we interpret the rate of change. But this is going to be important when we apply it to the regression equation and the relationship between our variables, I should say, x and y. So let's keep this in mind, and let's go back to the worksheet. So instead of y equals mx plus b, we use y equals a plus bx. And you could think of this as this is the same thing as y. And I'll talk about this little prime in a minute. So this little quotation thing there, we call that prime. And I'll explain why we use that in a minute. So we could also write this as y prime is equal to bx plus a, right? Order doesn't matter when we add, but it does matter which one is the slope and which one is the y-intercept, right? So you guys are used to y equals mx plus b, but instead of using m for the slope in the regression equation, we use b. So b represents the slope. And then the a is our y-intercept. Okay, so instead of m and b, we're using b and a to represent the slope and the y-intercept. We're just using different letters. And here's the formula. So we have 2 formulas in order to calculate b and a. Now, these formulas aren't difficult. They're just very tedious. They're time consuming if we're going to try to calculate A and B by hand. So we're not going to do that. We're going to rely on the calculator to give us these 2 coefficients, A and B. But I just want to explain what the formula is doing here. So if we look at B, we're taking the sample size and we're multiplying it by the sum of each x times y. So we take each x and y in each ordered pair, multiply them, and we sum them up. Multiply by n. Then we're going to subtract the product of the sum of all the x's, the sum of all the y's. And then we divide by the sample size times the sum of all the x squares minus the sum of all the x squares. And to get A, we would sum up all the y values and subtract B, the value that we got above, times the sum of all the x values, and we would divide by the sample size. So really what's happening here is that we're looking for the line, the equation of the line, that's going to best fit our scatter plot. Now, obviously, unless it's a perfect linear correlation, the line is not going to go through every single point in the scatter plot. But we want it to come as close to as many of the points as possible. So let me show you how to calculate our coefficients A and B for our regression equation, and we'll find the regression equation in this example right here. So let's look at example 7. So it says the data below are ages and systolic blood pressures measured in millimeters of mercury of 9 randomly selected adults. Find the equation of the regression line for the given data. So we want to come up with the regression equation that's going to best fit this data. And once we find that, we can make the scatter plot. We'll practice making a scatter plot with this one like we did in the previous lecture. And then we'll fit the line to it. And you'll see how nicely the line fits the data. So the first thing you have to do is we have to enter this data into 2 lists in the calculator. So I want you to enter the ages, so enter all the X values into a list, and then I want you to enter all the Y values into a list. For this one, I used L5 and L6, and you guys could use whatever list you want. But I want you to pause right now, and I want you to enter these 2 lists into the calculator. And then I'm going to show you how to find the regression equation for this data set. So now that everybody's entered their data into the calculator, and I'll show you where I entered mine. So mine are L5 and L6. So here's my 2 sets of data. And we're going to use the same function that we used in the previous lesson where we found R and R squared. It's in the same output. So we're going to press stat. We're going to arrow over to calc. And it's going to be option 8, just like we did last time in the previous example when we were looking for R and R squared. A and B are going to be in that same output. So 8, linear regression, A plus BX. Now this makes more sense, right? So this is going to give us the coefficients for our linear regression equation in the form A plus BX. So we're going to choose option 8. And put your X list. Mine was L5, so I have to change that to L5. My Y list was L6, so I'm going to change that. And again, leave the frequency list and store reg equation empty. We just need the Y list and the X list, and then we're going to calculate. And now you see, in addition to R and R squared, we have A and B, where A is the y-intercept and B is the slope. So let's round 2 places for both. So A is about 60.46 and B is equal to 1.49. So now I can write my regression equation. So remember, my regression equation is in the form y, again, I'll talk about the prime in a little bit, is equal to A plus BX. So in this case, so let's write it down, y prime is equal to A plus BX. We have A, we said was equal to 60.46, and B was equal to 1.49. So my equation is going to be y prime is equal to A, which is 60.46, and then plus B times X, or 1.49 times X. And that would be the equation, the linear equation that's going to best model age and blood pressure. And I want you to see it. I want you to see what this line looks like and how nicely it fits the data set. So let's go back to the calculator. Let's make a scatter plot of this data set. And we made a scatter plot in the last video. So we're going to do the same thing. We already have our data sets in the calculator. So we have to go to stat plot. So remember, we press second and y equals. Your plot is probably on from last time, so I'm just going to choose plot 1. Make sure it's on. We're going to arrow down to type, and the first one is your scatter plot. So we're going to make sure that's highlighted. And now we have to put our X list and our Y list. So my X list was in L5, and then my Y list was in L6. And now we're ready to graph, so we could press graph. And remember what I said in the last lecture. Most of the time when you graph, you're not going to see the points because the scale is not appropriate for our data set. So we just have to zoom stat. So remember, to fix this, we press zoom and then 9. So let's pick option 9, which is zoom stat. And the calculator is automatically going to adjust our viewing window for us so that we could see all our points. So you see that? So you see now I could see my scatter plot. So this is what age and blood pressure look like when we plot those pairs on the X and Y axes. And that looks like a pretty strong positive linear correlation, right? There's definitely a relationship between the two. So now what I want to do is let's plot that line on the same scatter plot that we have in front of us. So in order to do that, anytime you want to plot a line, we're going to press Y equals, which is the first button right underneath the window. And now let's enter that equation, that regression equation that we got, right? So Y was equal to 60.46 plus 1.49 times X. And X is right here. You see that red button that just got highlighted next to the green alpha button? If you press that, it'll pull up an X. And now just press graph again. And that line is going to get graphed right over our scatter plot. And see how nicely it fits that data set. So we call this the line of best fit. It's the regression line that's going to represent the best model, you know, for our data to model the relationship between X and Y. So I do want to do one more thing before we wrap up. I want to interpret the slope and the y-intercept in this equation that we have here, because I think it's really important. So let's interpret. So the 60.46, that's my y-intercept, right? So the 60.46, this is the y-intercept. And the 1.49 is the slope, right? So let's interpret the slope and the y-intercept in the context of this question. So remember, whenever I have a y-intercept, the x value is 0, right? And then the y value is whatever b is, or a in this case. This is what we're using for the regression equation. So the 60.46. Now, x is age, and y is your blood pressure. So this kind of implies, right, at age 0 when you're born, your blood pressure is 60.46. But now what happens as age increases, right? So now we want to look at that rate. What's the rate of change? So let's look at the slope. So remember, we always want to think of slope as a rate of change. So you want to look at it as a fraction. So anytime you want to make a fraction like this 1.49, put it over 1. Now remember, the slope represents the change in y with respect to the change in x. Now, y in this case is blood pressure, right? Whoops. Let me make this a little smaller so I could fit this. Okay. So this is going to be change in pressure with respect to the change in our x values, right? Where x in this case is age. And age we're assuming is in years. So what this is saying, both are positive, right? And which makes sense because the line is increasing. So for every 1 year, right, that we increase in age, so for every 1 year that we get older, we expect our pressure to go up, right? The systolic blood pressure increases. Well, by how much? 1.49 units. And that's how we interpret the slope. So I'm going to write that right here. So slope interpretation. So for every year an adult gets older, or we should say an adult increases in age, for every year an adult increases in age, their blood pressure is expected to increase by 1.49, and we're in millimeters of mercury. So by 1.49 millimeters of mercury, because that's the units that we were given in the problem. And that's how we would interpret the slope. So I think it's really important that you guys are able to not only get the regression equation to model the data, but to interpret it as well, especially the slope, right? So in this case, for every year an adult increases in age, their blood pressure is expected to also increase, specifically by 1.49 millimeters of mercury. Now, again, this is a model, this is an approximation. And that doesn't mean that for every year that an adult gets older, their blood pressure has to increase by exactly 1.49 units. This is just the model that's best fitting our data set, and we could use it for predictions, but it's not an exact science. So in the next videos, what I'm going to do is I'm going to do two different examples. So in the next video, I'll do another example where we're going to cover everything. So scatter plot, calculating R squared, the regression equation, and then I'm going to show you guys how to make predictions. So we have two examples, example 8 and then example 9, and I'll do these in two separate videos. Okay, so that's what we're going to do next.